Okay, so we're going to have a look at the mark scheme for the fats and oils test that you did recently. So question one was just a very simple question about making an ester. We were making butyl propanoate. So remember the first name here, the first part of the name is referring to the alcohol. Therefore it's butanol, and we would start off with that. Didn't say it was one butyl or two butyl, so you could have had either one butan-1-ol or butan-2-ol, and then it's propanoate, and remember that part of the name refers to the carboxylic acid, or acyl chloride you could have used. You could use, but you couldn't use in this question because it says organic acid. So that was, of course, propanoic acid with what we have here is butan-1-ol, and then remember it's this part here which transfers into the carboxylic acid, and the second part attached to the R group attached to the oxygen attaches to the alcohol part. So the alcohol remnant was, of course, the C4H9. And some of you did forget, maybe later on in another question, that there's water as a byproduct. Next question was name the catalyst in this. It was sulfuric acid, but you had to have the term concentrated in there. So a lot of you, it was only worth 1 mark, so a lot of you lost a mark because of that. Some of us got tripped up here by the skeletal formula, so make sure you refresh over skeletal formulas, the names of the reactants. So if we try and work out the carboxylic acid, so let's isolate the part which is the carboxylic acid, and remember that there's a carbon there, so that is therefore going to be the original carboxylic acid would have had that, so that would be ethanoic acid. A lot of us just saw this, forgot about the carbon here, said said methanoic acid. And let's look at the alcohol. Well, the alcohol would originally have had a OH. Okay, so this would have been the original structure of the alcohol. So we can see there'd be a carbon there, there, and there. So we would have a 1, 2, 3, 4, 5 carbon alcohol with an OH group on position number 2. So you had to say pentan-2-ol. When you're adding the catalyst slowly to the reaction mixture, when you're adding the catalyst, it's important to add it slowly. Remember, the catalyst is concentrated sulfuric acid in this reaction. Okay, going back to here, and you have to add it slowly to avoid too much heat being produced, which will vaporize the acid and vaporize anything that's in the flask, really. And secondly, it would dehydrate. Hot concentrated sulfuric acid is a dehydrating agent, and it would dehydrate your organic compound. Right, the next one then was a very simple reaction of sodium carbonate with the carboxylic acid. This is the way that you remove excess acid in organic preparation. The slightly concerning thing here was that some people actually got the formula of sodium carbonate incorrect, and really at year 14 that's fairly unacceptable, guys. So sodium carbonate is Na2CO3. We are removing from the solution propanoic acid. That's of course the formula of propanoic acid, and we get carbon dioxide, we get water, and then the salt is a propanoate to sodium in a 1-to-1 ratio, and you're going to need 2 of those and 2 of those to balance that equation. Now it's only worth 1 mark. It's a very simple equation. It's essentially a GCSE equation, so 1 mark is as much as you're going to get for it. Okay, when you're carrying out the purification, why is it important to open the tap and the separating funnel at regular intervals? Well, a gas builds up, but you have to specifically say which gas it is. It's carbon dioxide. Some people said a gas builds up. Some people said air builds up. Okay, you're not going to get marks for being not specific. Okay, and the reason, therefore, is you open the tap is to release pressure. That's the second mark, so some reference to that. Next question was, how would you safely, from the separating funnel, remove the unreacted propanoic acid? Let me just okay, yes, so sorry, so G has actually been changed. That has been changed and is now worded as how you would remove the non-aqueous product from the previous reaction in E. Well, the non-aqueous product, if you went back to E, you should have known that the non-aqueous product here is carbon dioxide, so it's a gas. A lot of us were talking about opening the the funnel, opening the top and allowing one of the layers to drain off. But the non-aqueous product is a gas, so you're inverting the funnel and you're opening the top. That's how you would get rid of the non-aqueous product, which is gaseous. Okay, question H then, we had to suggest something that we would use to remove moisture. So first of all, you had to say that it had to be anhydrous. That's anhydrous, believe it or not. Okay, so some of us missed out that word anhydrous. Calcium sulfate, calcium chloride, magnesium sulfate would have been another one. Some of you wrote calcium carbonate. That's a definite no-no. Okay, that reacts with any acid that would be in there to produce carbon dioxide, etc. Then we were asked the use of anti-bump granules. Anti-bump granules are simply to promote smooth boiling of the reaction mixture, prevent hot spots, spread the heat, something like that. The next one then caused a little bit of difficulty just because of the complexity of the ester. So you really need to I would suggest, if I was you, to draw this out. So it's 4-methyl 2-pentyl-ethanoate. So 2-pentyl would mean that I have 1, 2, 3, 4, 5 carbons in a straight chain. The 2 tells me that the ester bond is on number 2. Okay, and then the 4-methyl tells me that I have 1, 2, 3. On number 4 here, I have a methyl group, remembering that this carbon here is number 1. And if I cut that off, if you like, and I go back and I work out the structure of my alcohol, you'll see then that the alcohol is not just as straightforward as perhaps some of us maybe thought it was. Okay, so the alcohol has the OH group on position number 2, and then on position number 4, sorry, I've written an OH there by mistake. On position number 4, I have a CH3 group. So that's how you work out the structure of the alcohol that is involved in the formation of an ester. The rest of it was quite easy. It was ethanoate, so it's ethanoic acid is what you start off with. Quite a few here then, I guess you were a bit thrown by the complexity of the question, forgot to put your water in. Now remember, at A level this is only worth 1 mark, so if you got everything right and you left the water out, unfortunately you lost a mark. Right, this next question then explain 2 advantages, okay, 2 advantages, oh, sorry, this was an acyl chloride, sorry, so this should have been actually, excuse me, that's wrong, okay, I've written it for carboxylic acid. So that should be Cl there, and your byproduct then shouldn't be water, it should be HCl, but quite a few of us left the byproduct of that actually out. Okay, so your acyl chloride is just ethanoid chloride. Right, so you then had to talk about the advantages of making a carboxylic acid via this reaction instead of making a carboxylic acid with making an ester by this reaction instead of making an ester by using carboxylic acid and an alcohol. This reaction gives you a 100% yield. You don't need to heat it, and there's no catalyst involved. So those are the 3 advantages. A lot of people got the 100% yield. Quite a few people didn't get the other 2 advantages of using an acyl chloride and an alcohol to make an ester as opposed to a carboxylic acid and an alcohol. This time we had to write an equation for alkaline hydrolysis of butaidothanoid. So butaidothanoid has got a C4H9 group here, which will then, under alkaline hydrolysis, give us the original alcohol, which is butanol. Okay. The ethanoate part is here. Under alkaline hydrolysis, that gives us, remember, the salt of the carboxylic acid. So we get the sodium salt here. A lot of us had the actual carboxylic acid itself, but that's not what happens. Right, we had to draw the full structural formula of glycerol. Pretty much everybody got that right. Okay, you have to put your hydrogens on. I haven't, but you have to. Systematic name of glycerol, a lot of people got this nearly right. It was only worth 1 mark. A lot of people still leaving out the E whenever we have more than 1 alcohol functional group. Okay, it's cost you a mark. State and explain the solubility of glycerol. Well, glycerol is very soluble, you've got a mark for that. It has a short chain, you've got a mark for that. And it's 3 OH groups which can hydrogen bond then. Okay, so those were the specific things that you had to talk which were directly related to glycerol. You had to then draw a triglyceride. A lot of people were, in fact, almost everybody got this correct. Okay, 1 person I think got this, ended up with this single bond O here, which was, I think probably the only mistake. Alright, but it did ask you had to have one molecule of the oleic acid and you had to have 2 molecules then of the stearic. So I don't think you need a pile of help on that, but if you're not sure where you went wrong, come and see me. Name the process by which margarines are nowadays made in preference to hardening of liquids. Well, a lot of people got transesterification. Okay, a lot of people left out intermolecular transesterification. Okay. This one then, we had to take this molecule here, which was sunflower oil, and we had to work out one of the esters that we made when we make biodiesel. And if you remember, when we make biodiesel, we're making either the methyl ester or we're making the ethyl ester, one of the two. So we had to chop this molecule here, here, or here, and we had to then take, let's say, that chain there. Okay, and instead of having this group here on it, we then had to convert it to an O with a CH3, that would be the methyl ester, or with an ethyl group as so to there. Either of those would have given you the methyl or ethyl ester of sunflower oil. And you can use either that chain, that fatty acid chain, or that fatty acid chain. It didn't matter. And you could condense them down, decide them to condense down there to C17H33, or you could have just drawn them out as they were in the diagram. Right, next thing then, state 2 differences between the physical properties of sunflower oil and the ester that is made. Right, sunflower oil up here is a massive molecule compared to the ester. Remember the ester, and I'll just tidy this up a little bit. Remember the ester will end up as an ester of that, and that. So we'll end up with 3 separate molecules, and then the glycerol will be made on its own. Okay, so the esters are much smaller molecules than sunflower oil, so they're going to be much less viscous, okay, because the intermolecular forces are much weaker. It's going to be much more flammable because they're smaller, they're more volatile, they're easier to turn into gas and combust, and the ester is going to have a much lower boiling point and melting point. Okay, I think a lot of people actually got those the wrong way around. So remember the esters, this is the ester here, for example. Okay, it's only approximately 1/3 of the size of the actual sunflower molecule triglyceride in the sunflower. So the van der Waals forces are tiny in comparison. Okay, classify the type of ester. Well, this is a triester. There's 3 ester groups in it. It's a triester, simple as that. Okay, an equation then for the production of polyethylene tetraphthalate. Well, you had to have ethan 1,2-diol, you had to have your 1,4-dicarboxylic acid. There's your repeating unit. You could have had in here, if you wanted, your benzene ring. Sorry, a better drawn benzene ring than mine, preferably. If you want it, didn't matter. Okay, but a lot of us again missed out our water molecule, guys. So please put your water molecule in. You only needed 1 repeating unit, okay, so you didn't have to go overboard. Predict whether ethyl methanoate would be soluble in water or not. Yeah, it would. Ethyl methanoate would be this structure here, okay. So it's a very short chain. It has this region here, which if you remember from aldehydes and ketones, okay, itself can form hydrogen bonds with water molecules. Alright, and it has a short chain. So it can form hydrogen bonds via the COO that we have on it, and it's a short chain. So there's your 3 marks. Then we were into the calculation, which caused a lot of difficulties. Okay, you really need to practice these as you go through papers, guys. So we've got 12.5 cubic centimeters of an ester as that mass. So what's the significance of that? That will allow us to work out mass equals density times volume. So that allows us to work out the density of that. Okay. Whilst 13.6 of the propan 1-ol had a mass of 10.936. Again, that's going to allow us to work out the density of the propan 1-ol. We've got to make this amount of ester, which is given to us in volume. But if we use this value here to work out density of the ester, and we've now got density of the ester here and volume of the ester, we can now get mass of the ester. And if we can get mass of the ester, we can get moles of the ester that we need to be made. Okay, if we can get moles of the ester and we know the equation, okay, which we should do because it is propanol plus our benzoic acid. Okay, benzoic acid. Alright, so which would just be that with that there, and then our propan-1-ol will of course be that. So you should be able to work out the structure of the reactants that you start with, and they will react in a 1-to-1 ratio, and they will give us 1 mole of that. Alright, so what we've got so far, we have been able to work out density. Okay, from here we've been able to work out density of the ester. Now that we've got volume of the ester down here, we can work out mass of the ester. Once we've got mass of the ester, we can work out moles of that ester. When I get moles of the ester here, okay, so let's say it's X moles, I can then backtrack and I can get, as a 1-to-1 basis, moles of the benzoic acid, and I can get moles of the propan-1-ol. But remember, it tells us that there's an 85% yield only. So what I would do is take X here and multiply it, that's X times, okay, 100 over 85, or divided by 0.85, yeah, it's exactly the same. And that will scale me up to my 100% of moles. We'll call that Y moles, okay? So therefore, now I've got Y moles of that, is what I would have to start off with, okay? And the same number of moles will be true for there. Y moles of that is what I would need to start off with, okay? So it asks for the mass of the benzoic acid. Once I've got Y moles of benzoic acid, I just multiply that by the RFM, and that would give me my answer, would give me my grams. The answer will pop up on the next screen, by the way, so okay, I'm just explaining the method here. That will give me grams. Once I've got Y moles of my moles of this, I multiply that also by the RFM, and that will give me mass of that. Now we're looking volume of this, but if you look up here for the propan-1-ol, it gives me mass equal to a certain amount of volume, which allows me again to work out density of the propan-1-ol. And then it asks me down here to get volume of the propan-1-ol. Well, I've got mass of the propan-1-ol now, okay? So mass divided by density over density, which I can work out from the information in the question, gives me the volume of the propan-1-ol, and that would have been your final answer. So I'll pop the answer up here. This on 2 slides. I'll put it up now. That's for the first part, just to work out everything about the ester. So if you pause that, if you want to work your way through that, and then I'll pop on to the next slide, which has the final parts of the calculation. So pause this now. So those are your 2 actual answers that you should have given in the question there. Okay, so I'm going to leave it there, guys. Any queries or questions, please bring them to me, come and see me. Okay, and we'll get them sorted out.